So here are some steps for drawing Lewis and VSEPR structures. The first step is you're going to calculate the total, it's important that it's total, number of valence electrons in the compound. Remember that you use group numbers on the periodic table to do this. Number two, you're going to determine the central atom. Central obviously means the one in the middle. To tell which one's the center, it's the one closest to carbon. You're going to use some logic here. If there's one element and four of another element, it's obviously going to be the single is going to be the central. It is possible to have two central atoms. So if you have two carbons, for example, they would both be considered central atoms. Number three, you arrange the atoms and combine using lines. A single line is going to represent a single bond, double line, double bond, and triple line, triple bond. You add pairs of dots, which are called unshared pairs of electrons, to outside atoms first. If you have extra dots then to fill in your valence, then they go in the middle. All valence electrons from your calculation in number one need to be shown as either bonds or lines or dots. If an unshared pair is on the central atom, that is where the VSEPR comes in, and you would bend the bonds away from the unshared pair. Remember, the unshared pair is somebody that the other atoms want to get away from, so the bond will bend away. Otherwise, you're going to remember that the bonds want to be as far apart as possible. You want this whole even-steven aspects where all the bonds are evenly spaced. Unless there's an unshared pair on the central, then they're going to change their shape to get away from that unshared pair. So if we look at number one, we're first going to calculate the total number of valence electrons. And remember, we're going to do that by adding the total number of valence from each element, and you find that using its group number on the periodic table. So carbon is in 4A, so it has 4 valence electrons. Hydrogen is in 1A, so it has 1, but since the subscript of 4 is there, you're going to multiply that 1 by 4, and you're going to get a total of 8 valence. So either in lines or bonds, or lone pair dots, you need to show 8 valence electrons in this structure. So you see we have 1 carbon, 4 hydrogens. So we're going to use our logic, we're going to use kind of our general knowledge of bonds to see that carbon's going to be in the middle. That's the central atom. And the most even way to add 4 hydrogens is to do the cross. And then your last step in the structure is to make sure it has the correct number of valence electrons. So what you're going to do there is you're going to count how many valence electrons it has. Remember, this line here represents a single bond. So there are 2 electrons here. So it's 2, 4, 6, 8, 8 valence. We're good to go. So next we're going to do HCl. Again, your first step is calculating the number of valence using the group number. So H has 1 valence, chlorine has 7, for a total of 8 valence electrons again. Now, since you only have 2 atoms here, there really isn't a central, they're just 2. So the easiest way to combine 2 atoms would be a single line. And then your last step, you have to make sure you have 8 valence electrons, but here I'm only showing 1 bond, 2 electrons. So I have 6 more electrons that have to be added. Remember the octet rule. That's what's going to help you figure out where the electrons go. The octet rule means that each atom wants to have 8 valence electrons in its shell. The only exception is hydrogen only needs to have 2. So in this case, I do have a hydrogen atom. Hydrogen only needs 2 valence electrons. So right here, these 2 in the bond, that's good enough for hydrogen. Remember, these bonded ones, since it's covalent, belong to both. You count them in both. So the hydrogen's fine, it has 2. The chlorine, however, only has 2. So we're going to have to add dots around the chlorine to show that those are unpaired electrons. But then once we do that and we do our total count, we have 2, 4, 6, 8. So you're going to add any extra valence to atoms in order to complete what we call the octet. Okay, same thing with number 3. We're going to start with number of valence. So we're going to start with N, which is going to be 5. And then we're going to do 3 times hydrogen, which is 1. The 3 because of the subscript. So we get, again, 8 total valence in the structure. Again, to determine the central, it's the one closest to carbon, or logic tells you if you have 1 nitrogen and 3 hydrogens, the nitrogen will be in the middle. Then if we're going to combine 3 hydrogens and we want to make sure it's even, our initial structure would probably look like this. This is how the bonds are evenly spaced. It kind of looks like a fidget spinner or an, a triangle. Again, we have to make sure we have the right number of total valence. So right here, we have 2, 4, 6. I need 8. I'm missing 2. So where they go is where you use the octet rule. Remember, the exception is hydrogen just needs what we call duet 2. So this hydrogen has 2, good, 2, good, 2, good. The outside atoms are fine, but this nitrogen, since it only has 3 bonds, has 2, 4, 6. It needs 2 more. So what happens here is these electrons go on the central atom. Remember the VSEPR rule. As soon as those electrons go there, these bonds get pushed away. Think of it like a little force field that's pushing away the bonds. So what we have to do is we have to go back and we have to change the structure. So this is on a quiz or a test. Just go ahead and cross it out. So if you even want to, you can just say, nope, that's not it. I redid it. It doesn't work. So now what I'm going to do, N is still in the center, but since it has 2 valence electrons on it, the hydrogens push away. Now, don't worry too much about your exact angle of bonds or them being completely even. But what just happens is here, this lone pair on the central atom pushes all the bonds away, and then that's the shape. Okay, number 4, we're going to start again, just like we've been doing, totaling the number of valence. So we have 2 times 1 for hydrogen and 6 for oxygen, for again a total of 8. Since I have 2 hydrogens and 1 oxygen, oxygen's going to be in the middle. Now I'm going to do a little bit of calculation beforehand so I don't have to cross out and redraw. I'm going to try to draw it correctly the first time. So if I surmise that I'm going to have 2 bonds, because I have 2 hydrogens, so 2 bonds, 1, 2, that means only 4 electrons are going to be occupied in bonds. I need 8. And I know I can't add extra electrons to hydrogen because I only need 2. So all of that info tells me that the extra 2 electrons are going to have to be on the central atom. They're going to have to be on the oxygen. So if I draw them there first, then I know my hydrogens bend away, and then I get a complete structure because now I have 1 hydrogen, 1 oxygen, 2 hydrogens. I have 2 bonds. And I have 2, 4, 6, 8 electrons. And since these electrons are on the central atom, they move away. Remember, you don't add them to the hydrogens because they only need 2. Okay, last one is CO2. So we're going to do the total number of valence first. So we have 4 for the carbon, 2 times 6 for the oxygen for a total of 16. So right now, there's a couple of red flags that should be going in your head. 16 electrons is a lot of electrons, especially if you only have 3 atoms. Because if you have 3 atoms, technically you should just have 2 bonds, and that's a lot of extra electrons. So that should be going, Remember that I also gave you the little phrase of cons, C-O-N-S. Cons is the atoms that tend to form double bonds. So I have carbon, oxygen, nitrogen, sulfur. So the fact that I have carbon and oxygen who both like to form double bonds, and I have 16 electrons to take care of, what I'm going to surmise from that is the oxygens are actually double bonded. Because when I do that, now I have 2, 4, 6, 8 electrons shown, and I only have to include 8 more dots. So again, C-O-N-S, cons. Those are the elements most likely to form double or triple bonds. I do have 8 more electrons I have to add. Where they go depends on the octet rule. So if I look at the carbon here, remember each line represents 2 electrons per bond. Carbon has 2, 4, 6, 8 touching it already. So carbon does not need any more. But if I look at the oxygen here, it only has 2, 4. This oxygen has 2, 4. So the extra 8 electrons are going to go on the oxygen on each end. Remember, even Steven. So you wouldn't do this because that makes the molecule kind of uneven. You would do it even on both sides. If we want to get technical, and it's okay, you don't have to do this, but if you want to be most technical and most correct, they actually do kind of like Mickey ears in order to move away from that double bond there. So they actually do that to be most even.